All right, guys, got another lecture for you here. Chapter 4, Electric Circuits and Schematic Symbols. Now, a lot of this is added content from the internet, the illustrations. I don't like that the illustrators are going away from standard schematic symbols. The symbols are close that you see in the X-ray schematic in the Carlton Adler Ballock book, but I really think it's a disservice not to keep teaching standard schematic electric symbols, because on the registry exam you have no idea what the illustration is going to look like, and it's likely going to be some variation of standard schematic symbols. And so just understanding standard symbols means you're better prepared for the registry rather than dependent upon one illustrator out of one book. I would encourage you to look up X-ray schematics from several different authors so you can get a general idea how the variation. They're trying to vary their illustrations slightly so they don't get a copyright strike. But electric circuits are supposed to be standardized in symbolic form. And so you're kind of at cross purposes with the rules you're trying to follow. So the pictures that I have for the standard schematic symbols, the circuit element symbols, are taken from the internet if I couldn't find them in the text. So, okay, so representative examples of the circuit element symbols, and then the name of it and a brief description of its function. Okay. And so I think I've got a list coming up on like the next slide or so. And it's like it's like 8 or somewhere between 8 and 10 simple circuit elements and symbols that if you memorize these, you basically have memorized all the components of the X-ray machine that you need to learn and understand. And so recognizing them by symbol and being able to name them and describe its function, that's about all we can really ask about. Okay. And so after I introduce the symbols that I'm going to talk, I tack on the induction motor, and I think I got a nice video for that, and the generator because they mention it in the text. You're not going to be asked about electrical generators on the X-ray exam, so just for continuity with the text, I donate a couple slides to generators. You are going to be asked about motors, specifically the induction motor that I have the video embed for. So now, of course, with this recorded lecture, I'm going to skip over the video because it makes it troublesome as far as uploading it to YouTube. So, all right, so here are the schematic symbols that we need to understand in order to understand an X-ray machine, okay, or the diagram of an X-ray machine. Resistor, rheostat, which looks, at least that left-hand symbol looks similar to a resistor, and there's a reason for that. Switch, battery, ground, AC generator, so the source of AC power, voltmeter, ammeter, diode, and capacitor. Okay. The only one missing from this lecture, I think, needed its own lecture, and that's the transformer, and that is in fact the next lecture in the physics course. All right, so we'll start with a resistor. Now, we did say resistance was a property of the wire, okay, or the material we're using to conduct, okay? But a resistor as a circuit element is a specially designed section of wire. And the way they used to make this is they would just take part of the wire they were going to use for the circuit, and they would heat it up in a charcoal fire. And when the copper starts to get warm, the copper atoms start moving around and jiggling and creating space between themselves, and the carbon from the charcoal can actually weed its way into the copper metal and creates an impurity. Well, carbon has 4 valence vacancies, and it likes to covalently bond. And so it can scoop up 4 free electrons every copper atom, or every carbon atom rather. So if you put carbon atoms in the middle of copper wire, that section of copper wire is not going to allow electrons to flow through as much because the carbon is going to try to capture 4 of the electrons. Okay, and then it will have a full valence shell and a -4 charge, and it will start resisting more electrons coming through. Okay, so the more carbon you infuse, the less the conductivity of that section of wire. So that was the way that they first did it. Okay, modern resistors are actually ceramic cores with thin layers of carbon and metal films. Okay, so very much like a voltaic pile, but different materials. And the principle is not to build voltage or charge difference between these different layers in the resistor. It's to build resistance difference. And so the electrons trying to pass through the thin layer of carbon are going to be offered resistance. The more carbon you have, the more carbon layers you have to your resistor, the higher the resistance. And so they basically engineer resistors now. And they color code them. And if you're an electrician, you need to know the color codes. And the color codes indicate the amount of resistance that the particular resistor offers. Okay, and you can get them in a wide variety of strengths. Okay, which leads us to the rheostat. The rheostat is a variable resistance device. Okay, and the easiest arrangement of a rheostat is an array of resistors with a multi-point selector switch. And so you just stack resistors of different magnitudes, but then with a switch, you only allow the current to go through one of the resistors at a time. And so you're selecting resistance by changing the multi-point selector switch. You might have encountered a multi-point selector switch before. It's a television knob. So turning the channel on an old TV, that was a multi-point selector switch. Okay. It might not have been a rheostat. You've also encountered a rheostat. A dimmer switch on electric lights, that's a rheostat. And also your stovetop, the dial that you turn to make the burner hot or medium heat or low heat, that's also a rheostat. Okay. Rheostats manipulate Ohm's law. By varying the resistance with a constant voltage, we can affect the output current. We can either scale up the output current by offering low resistance or scale down the output current by offering high resistance. Switches. I don't have to explain switches. Give me just a second. All right, sorry about that. Mr. Shepard was going somewhere and I wanted to check in with him. So a switch, you know what a switch is. You flipped on lights before. A switch breaks the circuit, okay? So in order for electricity to flow, we need free electrons, we need a voltage, but we also need a closed loop so the electrons can get back around to where they started from, okay? If you break the closed loop, you take away one of the 3 things you need for electricity. And so a switch just does that. It breaks the closed loop. So when the switch is open, like it is in the diagram here, and that's how you always draw it, the circuit is off because the electrons can't jump across. You've broken the conductive pathway, and so the electrons can't jump across. If you close the switch, then the switch is on and electrons can flow. And so turning the lights on is actually closing a switch. Turning the lights off is actually opening the switch or breaking the conductive pathway. Okay. Now a circuit breaker is an automatic switch and it's tied to an ammeter. It doesn't show the ammeter in a diagram, but typically for circuit breakers as a safety device, It's a double switch on both the inbound line and the outbound line, or what they would call the hot line and the ground line if you're an electrician, okay? Or the hot and the return. A circuit breaker monitors the circuit for current, okay? And it opens the switch when the current gets too high, which is overload. Overload, that is a current that gets too high, can cause an electrical fire, okay? And so before that happens, modern electrical theory is built with safety in mind, because early electricity did not have safety in mind. You can look up on the internet how many house fires Thomas Edison's grid in Manhattan caused. And that's because he didn't have safety mechanisms like fuses and circuit breakers. So we found out very quickly electricity that runs to overload, that is too much current, can cause combustion. Okay? Those electrons are going to go somewhere. They are going to increase temperature. Okay? And so by breaking the circuit, we prevent fires. Okay? Now, I did mention fuses. Fuses were, before we invented circuit breakers, we invented fuses. Fuses were just thin filaments of copper wire that would melt and break, but it'd be in a glass cylinder such that it wouldn't cause a fire in the rest of the house. So your grandma had fuses. You probably still have fuses running to your hot water heater. Here in America, we have 60 and 120 gallon tanks for hot water. And that water gets heated up. And if the current overloads to the water heater, that becomes a bomb. It turns into a cylinder that starts filling with steam under pressure, and it can explode. Okay, and so water heaters are still wired with fuses, and the fuses will blow before current is overloaded in the water heater. Okay, the problem with fuses is once they blow, you have to go and get a replacement down at the hardware store. Whereas a circuit breaker, you can reset it. You can flip the switch back to on once you have determined everything is safe. Okay, so circuit breakers guard from surges on the electric grid coming from outside the hospital, but they can also guard from, in a limited sense, they could guard from surges that are created by using transformers. Transformers can also go runaway and produce surges of electricity. Okay. All right. Next one is a battery, and the battery represents the voltaic pile, which was that's where we first classified the battery as a device. Yes, there were Leyden jars, and they knew that they acted like batteries, but Alexandre Volta is credited with the voltaic pile, and I think it's because he understood what he was doing, and that's where the term voltage comes from, is from Alessandro Volta. The voltaic pile, you can make one at home. You just need some vinegar, some zinc plates, and some tin or copper plates. You stack the plates in alternating elements, so tin, then pour some vinegar down, then some copper, and then pour some vinegar down. If you put it in a bucket and submerge the whole thing in vinegar, that works the best. Connect one wire to the tin plate at the bottom of the stack. Connect the other wire to the copper plate at the top of the stack. The water will start bubbling. That's hydrogen gas. Don't breathe that in, and don't have an open flame next to it. But you will conduct electricity out of this bucket. Okay, and that's exactly what a Leyden jar was. So the crudest battery is a voltaic pile or a Leyden jar. Modern batteries have insulating shrouds, and they have impurities in them to keep the chemical reaction from going too fast and having a constant rate of the chemical reaction inside the battery. What's happening is, I don't know if it's the zinc or the tin, but one of them is donating an electron through the acid to the other one. Okay, it's a chain. I think it's two chemical reactions. One at the tin between the acid and the tin, and then another one between the copper and the tin. And the net result is an electron jumps from the tin to the copper, or from the copper to the tin. I forget which one is which. Okay. Um, so each individual section of cathode and anode, and that's what the long and short lines are. The short line is the cathode for deficit, and the long line, see, Franklin definition. The long line is the cathode or the anode for abundance. Um, and so each pair of those is called a cell. Okay. And you can stack cells in series to stack voltage. Remember, voltage is cumulative in series. So if you have one cell and then you stack another cell in series, on the left we have two cells. On the right we have 1, 2, 3, 4, 6 cells on the right. Both of those are batteries. Okay. The one is a 6-cell battery like you see in a car. The other is a 2-cell battery like you see in like a AA battery. Actually, AA battery is a single cell. But two AA batteries, like most of your toys and electronic devices take, handheld GPS, um, other type things, is a 2-cell battery. Okay, the more batteries that you stack, the more theoretical voltage you can create. Now there is an upper limit. You will create heat in the battery, and so you can't stack. Well, why not just wire, I don't know, like 10,000 car batteries in series? You're going to get a fire. You're going to get a fire because there is a connecting wire between each car battery. If it was one big battery, well, that would take up too much room. And if you connect the batteries in series, the wires that connect the positive terminal of one battery to the negative terminal of the are going to be pushing a whole lot of current because they're going to feel the push of all the batteries. And so you're not going to have wires thick enough, and you're going to create a fire. Okay. Yeah. So yeah, that's about it. And so the battery is symbolic of the voltaic pile. The short line is always the cathode end for deficit, and the long line is always the anode end for abundance. Grounding wire. Well, now we see abundance of charge, but then looks like it's diminishing and reducing. Yes, and so that's exactly what the ground wire is doing. A grounding wire is connection to the circuit to a source of infinite charge. Which sign? Either sign. This can be a metal chassis or connection back to the building's foundation. Or stick a piece of wire, or stick the wire into the earth. Okay? Dig a hole, put the copper wire in the hole, fill the hole back in with dirt. Okay? Grounds allow for the circuit to borrow or dump electrons as needed and to avoid overloading key elements of the circuit. So if we have a runaway current, a ground wire prevents a runaway current. You don't get a runaway current in a properly grounded electric circuit because the ground will take on the excess current. Okay? AC power supply, pretty straightforward. Here in the United States, we use 110 to 120 volt alternating current at a frequency of 60 hertz. That's 60 cycles per second. Okay? In alternating current, electrons cycle back and forth in both directions along the conductive wires to create electricity. Okay? And so we just show a sine wave bounded in a circle. Okay? DC is typically represented by battery or just a flat line with a pulsed line on top, a dashed line on top, inside a circle. Okay? Meters. I talked about meters in the last lecture. Um, and so this is the answer to why do you need to learn circuit geometries and why do you need to learn that current is constant in series. If we want to predict the current going across the X-ray tube, we need to wire the ammeter in series because whatever it measures at the ammeter, it's constant and the X-ray tube's wired in series to it. So whatever we read on the ammeter wired in series to the X-ray tube, where there's only one pathway between the X-ray tube, the power supplies, and the ammeter, and the electrons must go through that pathway, then we get an accurate estimate of the tube current. So ammeters wired in series because current is constant in series. That'll be very handy in answering if you remember those two principles, and you get you're going to get a diagram of the schematic, and it's going to have a voltmeter and an ammeter, and you have to tell which one's which. Well, which one's wired in series? The ammeter. Which one's wired in parallel? The voltmeter, for the same reason. Voltage is constant in parallel. So if we want to measure the voltage across the X-ray tube, and that's done at the pre-reading voltmeter, and we'll learn about that when we cover the schematic, you wire that voltmeter in parallel to the X-ray tube. And then whatever you measure on the voltmeter is the same because voltage is constant in parallel. Okay. Ammeters and voltmeters are represented by these symbols here. Okay. And so accurate predictions of both current and voltage elsewhere in the circuit, these meters have to be wired in correctly. Into the circuit correctly, not incorrectly. Okay. Diodes. The Franklin current comes into effect here or adds to our understanding of this symbol. Okay. Now this is a point contact diode, but it also has a black arrow in it, okay, which is a happy coincidence. Notice that the black arrow is pointing from positive to negative. Okay. So the diode literally tells you the direction of allowed Franklin current. Okay. The black arrow is always pointing in the direction of Franklin current for a diode. So the positive charges for this diode can flow from left to right. They cannot flow from right to left. So the electron flow can flow from right to left, but not left to right. Okay. So a diode is like a one-way street in your electric circuit. Diodes are going to be used in the rectifier. We'll talk about the rectifier when we talk about transformers in the next lecture. All right, so this is our first embedded video. Not going to play that embedded video because it'll mess up this recording. But that is about solid state semiconductor diodes, okay? And so we use semiconductor material in modern diodes. We don't use a point contact diode anymore. It's rather inefficient compared to semiconductors. So semiconductors are doped, that is, we add impurities to the semiconductor. Okay, sorry, interrupted again. So there's two ways to add impurities, and so we're going to use a base material of silicone. And we can add an impurity like, I think, gallium. And then it's basically other elements in the next family over in the periodic table. So let me pause and give you some representative elements that we might use. Hang on. Yes, gallium, if we add some atoms of gallium to silicon, well, that's going to have one less electron in the valence. And so it's going to create an additional vacancy. And that's p-type doping. Okay? And so there are holes available for more holes available for electrons to jump into in p-type. Okay? If we add a dopant like phosphorus or arsenic, though, then we get N-type doping. N-type doping means that there's an extra valence electron in the material, more than silicon. Silicon has 4 valence electrons. Okay, and so in N-type doping, you create an abundance of charges that can be motivated to move. In P-type doping, you create vacancies in the valence of the molecules in the material that electrons can jump into. Okay, and so if you line these up the right way, the free electrons in the N-type will jump into the holes in the P-type, and then they'll be replaced by more electrons from the wire, from the current wire. Okay, but if you wire them up the wrong way, backwards, then the holes separate and they don't go to the junction. The holes go to the far end and the spare electrons go to the far end, and they don't join in the middle. And so the extra electrons in the N-type can't jump across to the holes in the P-type if the charges are separated. So because of the special chemical properties of these two semiconductors, in one situation it conducts electricity, but just reversing the voltage causes it to not conduct electricity. Hence, semiconductive. It has to have the exact right circumstances to conduct electricity. It's a very handy and useful situation. And we will see, and you'll notice by the video, he's talking about transistors, which are a little bit more complex than diodes, but operate under the same principles. Transistors work like switches that you don't have to manually operate. They are semiconductor switches that can be toggled by applying a voltage or not applying a voltage. And so they're really neat. They take this concept one step further. We'll learn about transistors and digital imaging. And so I might have to do a set of digital imaging recorded lectures too. All right, and then we get to capacitors. Now, capacitors are not used, they are used in some X-ray machines, but they're more often used in mobile portable X-ray machines that you take around in the back of a hatchback or a van to nursing homes and skilled nursing facilities. So the capacitor kind of replaces the high voltage transformer. There is still a transformer in that X-ray machine, but it's much smaller. Okay, and instead of getting high voltage from a high voltage transformer, you do have a step-up transformer, but you just keep stacking stored voltage in an array of capacitors. Okay, and then when you make the exposures, you bleed out the stored voltage as extra charge on the line. And so tube current is maintained, but voltage is sacrificed. So, and I think the book talks about a capacitor discharge, you get a drop of voltage as soon as the capacitors are bled out of charge. So in a capacitor discharge machine, the simplest capacitor is two metal plates that are very, very close together with an insulating material or a dielectric material in between them. And so dielectric materials are not charged. They can act as grounds or they can act as insulators. Okay. So if I stack positive charges on the one plate, you would think that by Coulomb's law in a small distance, they would arc across to the other plate where the negative charges are. And so you would think there would be arcing from this, but if you put an insulating material in between the two plates, there's still electrostatic attraction, but there is no arcing between the two plates. Okay, so you wire these in parallel and they act like batteries to ballast the voltage and supply extra voltage as needed. You can store voltage until you need to use it, and then you bleed it back out of the stored charge of the capacitor. Okay. Motors. So they do a great job of representing Fleming's rules. And so the rule for a motor for Fleming is the left-hand motor rule. So you have to remember that this person's left hand is connected to an axle going through their second metatarsal or metacarpal phalangeal joint. So if the magnetic field is pointing forward and the current is running in the direction of the third finger, as shown in the diagram here, the motion of the mechanical rotation is going to be upwards, but if the whole hand is tied to an axle, that motion is going to become a circular acceleration. Okay, and so by creating this arrangement in an electric device, you can create circular motion. Okay. So motor configurations: DC motors have commuter rings, AC motors have slip rings. AC motors, the more common AC motor is the three-phase AC motor, which is not really well diagrammed here. The video does better than this diagram, but this is close to what you see in an AC motor. The commutator ring in a DC motor allows for the current to be reversed every half rotation of the motor. So it constantly pushes the spinning forward. Okay. All motors are created with a stationary outside and a rotating inside, and those are called rotors and stators. The stator is full of windings in either the DC or the AC that creates a rotating electromagnetic field, basically a rotating magnetic field. That's the whole job of the stator, either DC or AC, is to create a rotating magnetic field. Okay. The rotor in an induction motor is meant to experience the changing magnetic field. So Michael Faraday would say that the rotor has an induced current, and then Lenz will say that induced current will create a magnetic field in opposition to the rotating magnetic field. And so there will be a repulsion, but since the magnetic field is rotating, the repulsive force is actually a torque that spins the current carrying rotor. Okay. All right. And so DC motors are synchronous motors, okay, or can be made into synchronous motors, and synchronous motors spin at the same rate as the current. Okay, well, that's not a DC motor, excuse me. That would be an AC synchronous motor. An AC synchronous motor spins at the same frequency as the AC current. So 60 hertz, you get 60 rotations per second. That means the synchronous motor can be used as a timer, and early timing devices were synchronous motor timing devices. Okay, and then we discovered quartz and piezoelectricity. So modern timers use quartz timing, just like your digital watch. Okay. Induction motors. Induction motors are asynchronous, but they're variable speed. And so increasing the current increases the speed until, again, you create combustion in the wires, and you melt the wires in the stator. So you do have an upper limit to the speed, but you can vary the speed. You can put a rheostat basically in front of the asynchronous motor and effectively govern the speed of rotation of the motor. Okay. So this is a nice video Title of the video, Three-Phase Induction Motor Theory Animation Video. You can look that up on YouTube. I'm not going to include it in the recorded lecture, but I will be playing it for my students live. Okay. Generators. Generators will convert mechanical energy to electrical energy. They can produce direct or alternating current. You don't need to know about generators for the registry other than generators can produce either type of current. Okay. Typically, a generator involves applying rotational motion to a wire coil inside a magnetic field, or alternatively, surrounding a bar magnet with coils of wire and spinning the bar magnet inside. Okay, either one creates a changing magnetic field relative to the wire and so creates a current. Okay. The rule for generators is the opposite of the rule for motors. And so it's the mirror image of the left-hand rule. It's the right-hand generator rule. So again, if we put an axle through the metacarpal phalangeal joint, the magnetic field north is pointing to the left, and then the motion is that would be a counterclockwise rotational motion indicated by the thumb. Current will flow out towards you, the viewer of this PowerPoint, okay, out of the loop towards you. Three-phase generation employs an armature with three separate magnetic fields, three coils. Each of those magnetic fields are 120 degrees apart. So a complete rotation will produce three AC sine waves that are out of phase with each other. It's like the crest is shifted over on the timeline. Okay. It is the most efficient type of electrical generation, and it was invented by Nikola Tesla, and it's the way that we solved the fundamental problem in the Current War movie. And so when we watch the Current War movie, and this whole conundrum of spinning a motor with AC, Tesla is the one that figured it out. So a lot of your high power electrical devices run off of three-phase AC wave.